So everybody got their quiz uploaded? Was uploaded, everybody?
Yes.
Okay, anybody not have their quiz uploaded? Okay, let's get it uploaded, right? Okay, so you guys have a couple of assignments that pertain to you already. One of them was an introduction. Whoever asked you, what you just did, basically they had it written down. You guys are supposed to take a picture of it and upload it. Anybody not? Your introduction. Okay, so you need to do you don't have an introduction to class either. Oh, perfect. So you got lucky last week. So you can stand up and do exactly what you just did. And then what else you guys can do is write on a piece of paper because I'm old on this piece of paper, right? So if you guys can write on a piece of paper what you just said, right? The name, the major, what you can do, right? And then what you see some 5 years, then what do you want to do when you grow up? And the last thing is something you need to class. Okay, you got that?
Not really.
Don't worry about it. We'll walk you through it. Your name?
On the major, kind of going to centers. Trying to help us what to say or
Okay.
Yeah, I mean, the sound California. Yeah.
What? So you commute from Selma?
Yeah.
Are you serious?
Yeah. I'm struggling with the schedule. It's not my last one.
Okay. That was probably me. I actually go to Selma on practice. I teach there. Okay. It's different. What do you want to do when you grow up? So you think you may want to be a nurse, but you actually want to be an astronaut or a billionaire or
Like right now, she not really working, so I have make money outside. So it's something I have. So it's like I had the drawing, basically 5 hours.
and so you your group consists group projects. You guys talking about group project? Who wants to talk about group project?
So we have to do a video.
Oh, serious.
Now
It's serious. It's serious. Okay, so is anybody having any trouble uploading their assignments? Okay, so we've done at this point, you guys have done 2 labs. We're doing the third lab. And you see we're really running, right? We're going to be doing the third lab this week, right? The first lab was just a safety lab, right? You need to make sure that you fill out everything. There are a couple of you guys that emailed me about, why did I get this wrong? Well, if you have to explain, what do you expect me to do with it, right? I'm mark wrong. So you need to fill out everything, okay? And some of it is that it's intuitive. You should know that. We talked about what happens in the lab, okay? Yeah, you can resubmit. Yes. So if you have a bad score on it, you need to resubmit it. I'll make sure, let me know if it isn't open. I'll make sure it's open for me. I'll give you guys until Saturday to get those all in, okay? So your other lab, the Mentos lab, you need to answer all the questions that you can answer, right? We're going to use that to do a homework report, but I still need you to submit, okay? So you guys can be prepared for that. And a date, yeah. And a date. You you should have just written it right all on that page, because I don't have one way. See how you think, what you're thinking about. If you bring up five, or you put a leader out there, right? So like that, you one. Right, two. What's getting is one.
That's the raw data is time without energy.
That's the raw data.
Okay. Not the sheet, right? Not what we can put the sheet with other classes.
No, that's we need to talk about that too, right?
Oh, okay. I'm the best
Yeah, but no, and then you're supposed to make a table and all that stuff. Where do you do that? On Thursday, so part of the lab Thursday, the lab, working on the lab. Part of the lab is here. Okay. So, the last thing, you guys are gonna be writing a formal lab. Right? The formal lab is gonna be worth 300 points. We're gonna have 3 of them. So if we have 3 times 3, 300, that's 900 points. Normally, each of your labs are worth 100 points. So you guys will have the formal labs are going to be almost the same weight as all your labs that you've done throughout the semester. Right? So they're going to be heavy. Okay, now in the formal lab, you guys switch screens. Okay, the formal lab has to be typed. Right? So those typing steps work. You have to include the title. The title is going to be worth 50 points. Your purpose. What is the purpose? Moses, what is the purpose of the lab? Okay, so that in this case, that was for this purpose, right? So the idea is to basically learn about science, right? So we talk about the purpose of the lab in general. The purpose of the lab is why you're doing the lab. So the reason why we do this lab is primarily to learn about scientific method. Okay, so the next one is the hypothesis. So you guys all have your hypotheses, right? Yeah. No?
Yeah.
Yes. Yeah, you know the weekend has already passed, and this is like Monday, right? Because you guys are. Yeah. So we got to pump that up because otherwise it'll be a long night, right? Okay. So use Blake's hypothesis. Here, that did not sound like. Okay.
Anyway, Diet Coke would be the exploder, right?
So Diet Coke is.
I mean,
Diet Dr. Pepper is going to explode high. Okay, so that was its hypothesis. Okay, so we'll talk about whether or not it was a good hypothesis or a bad hypothesis. Okay, so you clearly state your hypothesis. Okay, then you want to show your data. Now, your data is that raw data. You know the stuff that you supposed to upload last week? That's your raw data. Okay, so you want to make sure that you show it, and I want it raw. So I want you guys to have a picture of it, right? In your lab report of your raw data. So the reason why we use our raw data is because it's like a reference. It shows us when you did it. It shows us that it was all, chicken scratch or whatever, right? And so that you didn't like fudge the results. So you always want to be able to provide your raw data anytime that you're giving a presentation or you're submitting something. You always have a copy of that raw data. And typically, when you're working in the lab, you write in pen, so you can't make those changes, which kind of sucks because I like to erase the whole lot. Okay, so you just like if something is wrong, you basically cross it out with one line, so people can see that you're not fudging the data, right? So how many of you guys remember working with tiny, right? So when you guys do your charts, you have to draw a single line to it, and often you're supposed to. Oh, that's right, it's all computers, that's true. So that's even better, right? Because it's timestamp, right? So that's true, everything is true. Electric conical rays. Great improvement, right? Until they're lost, right? Then that's the problem, right? Yeah, that's the problem. So in the old days, back in the Stone Ages, when we had to use those tablets and everything, right? So we'd often have to draw a line in it, and somebody would have to counter sign off. So I'm gonna make you guys go back to the old days. You're gonna have to, show that raw data. And then if you guys are doing it, you should draw a line in it so that we can see, right? Okay, so what is data, right? So data is a combination of what you guys are collecting, right? It's that height, it was the temperature, it was the pH, it was whether the litmus paper turned velvet or lavender or whatever color you guys are seeing. We have a lot of different colors. Right? So, and then observations are kind of like what we saw. Did you guys make any observations about the changing color of the soda? Any of the sodas? You guys see it? Did it ever change color? Okay, so it changed lighter pink. Yours changed lighter color? Yeah. Okay. Okay, so those are the things that you want to keep track of, right? And you guys did documentation. You took pictures, you took videos, right? So you want to sit there and show documentation of it as well too. So if you guys see those observations, you want to be able to document. Okay, now the results are basically printing up your data, right? And you're also using it to try to tell a story. Okay, so you're going to take your data and you're going to do graphs, or you're going to have to do some kind of calculation, or you're going to have tables or charts, right, to prove your point. You said your hypothesis that was that the diet was higher than all the rest, right? So then you want to show a table that shows us that the diet is all the rest, or that it didn't show that the diet is all the rest, right? Because either you're proving your hypothesis or disproving your hypothesis, right? And then you also want to give me a description of what's going on. You want to make sure that your table is labeled, because if it's not labeled, you can't tell what's going on, right? And you also want to kind of lead the reader. So it's clear that the diet was higher if that was the case, or the diet was not higher. Okay, so trying to flip things and flip it. Scroll up. The next section. Now, this is one of the heaviest weighted sections. You guys notice, right? Because that's the one that you're going to spend the most time doing. It's the pretty fun of everything, right? The next section is also a very important section too. That next section is the conclusion. So typically what I do is when I time crunch, I work all of the other stuff. I skip down to the conclusion, right? And then I'll take a look at your graphs, right? I want to take a look at all your text in your results section, because you should be explaining what's going on and what I should be seeing, right? To help me guide the reader through the process, right? So in this case, you're going to briefly state your hypothesis and your purpose of your hypothesis. You're going to evaluate your hypothesis. So what do I mean by evaluate your hypothesis? Was it right or wrong? Was it right or wrong? And you want to tell me why? Was it right or wrong, right? Because there could have been a reason why it was right or wrong, why you think it's right, right? The next one is, if there are any questions in the lab, you want to answer all of those questions. So you guys have already answered it. You've already done the hard work. Now all you have to do is type it up, because you guys did that last week, right? Okay? And then if there are unknowns, you want to identify those unknowns. In this case, there were no unknowns. Typically what I mean by an unknown, I'll give you guys, say you're going to have sample A, you're going to have sample B, you guys are going to have sample C. They're all three different types of metals. I want you to tell me what the sample A is. You tell me what the sample B is, and you tell me what sample C is by how they react in chemical reactions, right? And so you should be able to tell me what they are. So they say sample A is iron, sample B is aluminum, sample C is sodium, right? So then you clearly state what the unknown is. It's just one sentence, it's not that hard, right? But you have to tell me the code for it, the unknown, and what it is. Okay? Now, those we have unknowns. Those are going to add those points up more. So those points are going to add a little bit more to it because they're unknowns. You're telling me something that you didn't know. That's it. Kind of like a test. Okay. The next part is if something went wrong during lab, then I want you to explain to me why that didn't work. And so, for instance, last week, I believe, one of the groups had their test tube, they left their test tube on top of the soda as they dropped them into the city. And then they pulled it away. Didn't that happen here in this class? Didn't happen here? I could have sworn it did. Yeah. I'm pretty sure it was. Was that? So none of the Mentos fell out, right? So those are examples why, well, maybe it didn't go as high because it didn't get enough Mentos. Or in the case of, well, we dampened our height because we kept the cap on top of it. You know, I had a group, I think it was 2 years ago or something like that. So they put the buckets in and somebody screwed the cap back on, right? Oh, so, what happened? Well, nothing, right? It just kind of, it kept getting bigger, bigger. I was going to blow, but it never really cooled, right? So, yeah, so, but it didn't go high, right? You can't tell how high it went because, nothing was coming out. So, you want to explain why it didn't work, right? Why there were errors, right? If you guys repeated that experiment, it's okay, don't worry about it. But if you didn't get a chance to repeat it, because sometimes we are short on supplies and we can only do it once, or we only have so much time to try to get it done, then you can't repeat it. So then this gives you an opportunity to say, well, look at the experiment, so, so, and rather than you guys getting deducted for not doing the experiment, I know why the experiment. Okay? And then the last thing I want to know in your own words is why, or what is it that you learned? Not why. What is it that you learned? So explain what you learned. So what did you guys learn from this? So sparkling water doesn't change the Mentos. Well, what I learned from it is I'm not going to drink soda and eat Mentos at the same time. Right? Okay. So and the very last thing is talk about that extra credit, right? So you guys are going to get 5 points extra credit if you guys upload your video to YouTube, to let's see, Kick, to TikTok, to WhatsApp, which you guys see me related to, right? So I'm able to see it. So I want you to show it to your friends, right? That's the purpose, right? And it is one person, right? You don't get points if you load it, she's not going to get points, right? It has to be, everybody has to load their own because you guys have different friends, right? I would hope you guys have different friends because a lot of you guys don't seem like they're attached to the hip, right? So, okay, good. Okay, because we want more students. We want this, I want this class to be packed. I want it to be so tight that it's hot for not just because it's hot in here. It's hot because there's so many people, right? So, and I want the waiting list to be around the block. So, okay, questions? Concerns? Yes? Too late? Okay. Oh, I didn't tell you that. That's a good question, right? So the formal lab is going to be due, it's not going to be due this Saturday, you will have until next Saturday to get it done. So typically, you guys do it, and I say, this is going to be a formal lab, right? So then you guys will have a week to get it done. Okay, that's this formal lab report. It is a formal lab report for the mental side. Okay. We will be going over how to officially write it at the beginning of class on Thursday. Okay, and then we'll do our lab. Okay. So let's talk about this. We get answers? Everybody got answers? Everybody got answers. Okay, so what's the first one? What are the 4 items that you must have? Goggles, shoes, closed-toe shoes, yes. And a hair tie, that'll work if there's no more things you guys do. It says black coat, gloves, yes. Okay, what is the starting point for scientific method? Observation. Okay, Explain the difference between micro, macro, and particulate.
Micro, macro, particulate.
Okay. Okay. So, but actually, you can because these are very specialized.
Washington.
Okay. Piece of cake, not too hard, especially since you guys had your notes, right? Right. So, one thing is that we had to talk about that last one, right? But you guys are responsible for it because you should have read it, because I was chapters 1 and chapters 2. And everybody's read chapters 1 and chapters 2, right? I don't even have to talk about it because you guys have already read it, right? I'm just making sure, right? Okay. So for next week, you guys have chapter 3. So you want to make sure that you read chapter 3 because you're always going to have one question pushing over ahead. Okay? Okay, so let's get started. Have some fun.
We have to read
Chapter 3 because we'll be going over. And if you're attentively doing it, you're going to be well. If you're behind me, you're going to stop. Right? And typically, the way it works with the business, you got 5 days. Today I was very lenient, and I have to go and get paper downstairs. And, you know, but that's going to change because you guys got a lot to cover. Yeah, this much time to cover. Okay, so let's get started. So, matter is in everything. Everything has matter. Everything's made of matter, right? Light, everything. Okay. So, you guys already told me, if it's macroscopic, that basically means that we can see where our eyes. Right. So, if it's microscopic, it's a microscope. So, like a virus, or a plant cell, or an animal cell, right? That's virus kind of calls that. So, a particulate is so small that you can't see it with your eyes, or you can't see it with a normal light microscope. It costs $575, 55 cents. I gotta get money something. You got this one?
No, I haven't.
Okay, so because a particulate is so small, and particularly when we're talking about chemistry, we often will have to use models to represent it. So if you guys take a look, and I try to use my little laser card, I can do it. You take a look here, right? So this is just basically a simple perspective of methane. These are what methane is.
Methane?
Methane is the gas that comes out of cow's butts, right? So methane is often in farts. No, that's methane. Ethanol is pretty common. That's when you want to turn out. It's a little different. Right? You don't want to turn out smelling cow's butt. Just does not work, right? Okay. So anyway, because in theory, we'll draw this nice little stick figure of everything, right? We want to see what it kind of looks like. What is the shape, right? So we'll use a model to represent it. Because we can't see with our eyes. Okay? So this here is just a plastic model, so it's called the ball and stick model. Or you can just call the ball and stick model. Because there's balls and sticks, right? It makes sense. This one is called the space filling model. The space filling model is kind of give you a better representation of what's happening. So the way we bond it, you're going to have these atoms that are overlapping, and that's what it kind of represents. So it's filling that space, right? And this is just showing everything on top of it. So because we can't see it with our eyes, we have to use models to represent it. And so we will often use our chemical representations. We'll use symbols to they represent. So you guys have your periodic tables, right? Now, actually, all of we have to go over on the table, or on the periodic table. You guys are good at having a notebook here. Look at that, prepared. Nice tape, it's all nice and fresh. They don't smell like methane. They don't smell like methane. What should I say? Ethanol. They also like that either, so after you get out the water. Okay, so if you go to the periodic table, the periodic table has all of the elements or all the atoms that we know about, right? They're organized in a certain way. You guys look at the very top, there are numbers at the very top. You guys see those numbers at the very top? Those are called groups. Okay? You have numbers on the side. Those are your periods. So elements that are in the same group often behave the same way. Elements that are in the same group often behave the same way. One way or another, they behave the same way. So if you guys look at group, let's take 17. What's in group 17? Halogens. So we have, what is that? Chlorine. Chlorine. Iodine. Bromine. Acetylene. Okay, so all of those guys are in group 17. Now, group 17 is a very reactive group. They like to react. Those again are called your halogens. We talked about this last week when we talked about waste, right? Because they like to react, right? So literally, next to them is group 18. Group 18 is like the noble gases. The noble gases are like cool kids, right? Or the rich kids on the block. Or the prince, or however you want to think about it, right? They are the ones that have, right? They're stable, they're good to go. Now, everybody on the periodic table wants stability, right? How many of you guys want stability? Want a good job, want a good man, a good woman, both, right? Well, hey, hey, we are in a different society, it's okay now, right? So, the thing is that we want stability, right? We're always looking for some form of stability. I assume that all the reasons why all you guys are here is because you guys are looking for stability. If you guys were independently wealthy, most of you guys wouldn't be here. You'd be in, the Bahamas or in Alps or wherever you want to be, right? Spending all that good money, right? But because we don't have it, we're looking for stability. Now, the elements are exactly the same way, except for the noble gases, because they're stable. Everybody wants to be like the noble gases. So I can say everybody wants to be like the Johnsons. Well, noble gases are like the Johnsons. There are 3 ways that you can be like the noble gases, right? Now, you can either take, give, or you can share. Okay? And when we talk about take, give, and share, we're going to be talking about electrons. Okay? And we're going to talk more about what an electron is a little bit later. I just want you guys to understand. Now, the reason why things react is because they want stability. Right? Like us, we react. We're in school because we want stability. So that's the reason why we react. If you don't need to react, you're not going to want to do it. If somebody was going to take care of you, give you all the money in the world, would you be here? Right? You'd be like, no. Yeah, all you think, great, you're PD, right? You'd be like, you're good to go. So, reactions occur in cause. Okay? Now, we look at the periodic table, we'll notice how the elements are written. Either they're all a single capital letter, or they're a capital letter and a lowercase letter. Okay? So, you guys can all see it right away. So I'm going to switch back and forth real quick. So there's a tendency when somebody has never taken chemistry. I've had students that will go through the whole semester with this. And I'll talk to them about it. But let's say, for instance, we're writing P lowercase l, right? And instead, really, this is what they wanted to write was P O. Now, if you guys do me a favor, on your periodic table, can you tell me what capital P, lowercase o mean?
Polonium.
It's polonium. Okay? Can you tell me what capital P and capital O mean? Phosphorus and oxygen. Are they the same thing? No, they're not. Polonium and phosphorus monoxide are not the same thing. They're different. They're going to behave differently. So polonium is a radioactive element. It's slightly hot. You guys will be able to play with it a little bit later this semester once you learn a little bit. Right? So it's slightly radioactive. Where phosphorus oxide is reactive, but it's not radioactive. Right? And if you put this in, when you're planning to put this in, you may get a nice explosion, right? That you don't want to get. So it's really important that we write the symbols correctly. Another one that's often done is, let's see. Often they'll do this. I see a lot of this happening where they just write everything in lowercase, right? That doesn't mean anything, right? You don't know what that is. So you want to make sure that you're showing the symbols very correctly, because otherwise it can mean something entirely different. Okay? So, you guys are familiar with water, H2O, right? This is called the subscript, that number there. That subscript means that we have two hydrogens. Since there's no number here, it's understood that there's going to be one oxygen. So H2O, water, is composed of two hydrogens and one oxygen. They're written together because they're bonded. These guys are written together because they're bonded. This here is a single element. Okay? You guys listening so far? Okay. So if I have okay. So how many oxygens are in that compound? 2. How many carbons are in this? 1. Okay. Good. Now, often you'll see something written like this. Okay. Mg. Can somebody tell me what Mg is? Magnesium. N. What is N? Nitrogen. What is O? Oxygen. Okay. So when it's written like this, my voice is changing a little bit there. When it's written like this, what's in parentheses is double. So there's 2 of them, right? If there were 6 here, that means there were 6 of those that are parentheses. So really what's happening is that you have this Mg, and then you have 3 and N. And both of these are connected to that, right? Again, this here is considered one compound together, and they're bonded. Okay, and I'll tell you how they're bonded later. Okay, so if we look at this, how many nitrogens do we have? 6. 2, because how many's here? What's that number next to it? 1. Because it's understood to be 1. How many oxygens do I have? 6. How many magnesiums do I have? 1. Okay, so what we typically do is to keep us from having to write out like this, we just, you guys do distribution of that, right? We're going to distribute 1 times 2. It's 2, right? Okay, so we have 2 nitrogens. 2 times 3, 6. So we have 6 oxygens. And we have 1 nitrogen. So these subscripts help us know how many we have. Okay? Questions? Don't overwhelm yet. Yeah. Nobody's overwhelmed. That's good. I like that. Okay, so let's start talking about this as math. Do you guys know the mistakes of matter? Gas, liquid, and solid. Good job. Right? Gas, liquid, and solid. And if you guys are taking 1A, we talk about class. Right? So we're just talking about gas, liquid, and solid. So, what is the difference between ice, water, and steam? Listen. What was that? He said ice is a solid. Yes, ice is a solid. Water is a liquid, and steam is a gas. Okay? So, if I started off with a big old block of ice, and it's sitting in this room, what's going to happen? It's going to melt and turn into liquid. Why? Because of temperature. You said, what did you say before that? Heat. Heat. Okay, so let's talk about that. Heat is a form of energy. Right? So, us changing that temperature, taking that ice into a warm room, is going to cause it to melt. So we're changing states. So we put energy in so it would change states. So let's say we decide to sit there and heat up the room a little bit more. What's going to happen to that water? It's going to boil, and then what's going to happen? We're going to get steam. So what do we do to make steam? We put in more energy. We heat it up. Okay? So what's happened when we heat this up? Exactly. The molecules move more, right? Have you guys ever been to a beach where you have really, really hot sand, or been out on the street where it's really, really hot and you're barefoot? Okay. So, if you're going to that beach and there's cool water there, right? And that beach, are you gonna walk? You're gonna go to the water? You're gonna run, right? Because of what? Because of the heat. It's making you speed up, right? It works with us too, right? It speeds us up. So what happens is, when we put energy in, it causes those molecules to move faster. Fast, right? The difference is like what? Yeah. I got one person goes, you guys are lying. There has to be more than one person that goes to the right? You guys good parents? Well, you went on a date, so you can't talk about anything. Okay, so in the case of the nightclub is really packed. How you dancing? You never been to a nightclub? Boy, she knows. She's like, she doing this, right? Because it's tight, right? There's not enough room. So when we think about those molecules, right? When we're solid, we're really, really tight. Okay, so you don't have room, so you're just vibrating just a little bit. Okay, that's it, right? Now, the liquid has a little more room. So liquids are just, the line next to you can really get down, right? And then, in the case of the gas, you have a whole space to work with, right? The whole room, so you're just like, yeah. It's just getting crazy, right? So, that is part of the kinetic molecular theory, right? Molecules are going to always be in motion, whether they're frozen, whether they're static, or whether they're the gas. Not today. Okay? But the more energy you put in, the faster those molecules get. The more heat you put in, the faster they're going to move. Okay? And that's something that we want to keep in mind. Because if we're doing reactions, what do you think is going to happen? Is the reaction going to happen really fast in ice, chili? No. But if it's really hot, it's going to be happening really fast. Okay? Okay, so we're going to talk about society just a little bit, right? How many of you guys see methods? Methods. Just you can tell me like people that should method, right? On an everyday basis, right? So when you catch method in the winter, they're going to be a little bit different than they're in the summer. Have you guys ever noticed that? Oh, they're off like a chain. In summer, they are crazy, right? Now, don't get me wrong, they're kind of crazy in the winter, but they're a whole nother level. Why do you think that's the case? Yeah, it's taking a little slower, right? In the winter, when it's cold, right? When it's cold outside, it's taking a little bit slower than in summer. And summer, it's speeding up, right? So you can sit there and show this in society. Something like that happens, right? Pay attention to people. See how they act. I'm sorry, how they act in the summer and how they act in the winter. Okay, I get you, right? Okay? So, we talked about gases. Gases are going to be far apart. They're going to be bouncing off the walls, they bounce off each other, right? Liquids, they're going to be a little bit closer together, right? But there's still going to be enough movement to move. And then solids are going to be tight, they're going to be fixed, right? So solids, there are two types of solids. We have a crystalline solid, and we have a amorphous solid. A crystalline solid has arrangement, has a very defined path. It's organized. You know, it's like that add and tie group. So it's solid, right? And then amorphous is more like me, you know, they lack that shape. They got a little fudge here, a little fudge there, right? So amorphous, lacking shape. Okay? So we talked about it. This requires energy. Either we're going to be taking in energy or we're going to be releasing it. So I want you guys to help me out with this. If I go from a solid to a liquid, is that going to require me to put energy in to make that happen? Yeah, I can put some heat in, right? Okay, so that process is called melting. You're like, everybody knows that, right? Okay. So if I go from the liquid to a gas, right? We're adding more energy, right? Okay, so that's called boiling or vaporization or evaporation. Okay. If I go from a gas back to a liquid, that's called sublimation. Right? I'm sorry, deposition. Sorry, deposition. Okay? Gas, not gas, or back to liquid. Gas back to a solid. Deposition. Now, if I go directly from a solid to a gas, that's called sublimation. If I go from a gas back to a liquid, that's called condensation. Okay? And if I go from a liquid to a solid, that's freezing or fusion. Chemists, we call it fusion because we just want to make it hot naturally later on because we use it again for something else. Okay? So, this is just basically explaining all the things in the case of molecules, right? So, look at the shape. In the case of a gas, if it's a closed container, it's going to occupy that entire thing, right? You guys can see the molecules coming out of it and stuff like that. If it's a liquid, it's just going to be at the bottom of the container. If it's a solid, it's rigid. It's still going to be in the shape that it originally was in. The volume. You guys know what volume is?
Yeah, how much space it takes up.
That's right. Okay? So, volume, in the case of gas, again, is going to occupy all the volume you can take up. Right? So, let's think about this. So, in Virginia tubes. You guys know what I mean by tube? Yeah. Right. Breakaway. Pass gas, right? So, Virginia tubes, does it stay there? Right next to Virginia. What happens? It's a little weird too. Right? It's a little weird too. Right? It spreads, it diffuses. Right? So it diffuses, and eventually it will occupy the entire room. Everybody can smell it. Everybody can do this. Right? Virginia will be doing it too. She can play it off. Who did it? Because you know what I'm saying. You smelled it, you got it, right? Right? That's the rule, right? So nobody's going to say anything, right? Because everybody's like, what's it mean? So you're all looking around, right? So, but we know from experience, gas is going to occupy the entire room, right? We learned that very young. Okay. So, we know that those particles are moving, right? The gas particles are going to be moving because they're not connected. There's no connection that's going on with them. They're going to be totally random. They're going to be moving free, wild and free, right? Like I was saying, it's wild and free. Okay? Now, the water, there's going to be some connection. It's not going to be as tight, right, as the solid, but they're still going to be connected, right? And there's going to be movement. There's going to be independent movement and stuff. And then in the case of the solid, you're just getting a little bit of vibrate. A little bit, right? So the speed, very fast. Particles are, right? In this case, you're going to have particles that are going to be able to interact with each other. That's what's going to keep them in that negative state. You have that little bit of interaction, right? And in the case of the solid, you're going to get very, very strong interactions, right? So you're going to get very, very few particle movement. It's going to be very tight. Because that's pretty good so far? Not too hard? Okay, so all of this represents physical change. Physical change. So the way that we look at physical change, if I can go, and I want you to tell me if I'm wrong. So I have a thing of ice, and I melt that ice, right? And I collect it in the middle. Okay? And then I take that ice and I boil it into steam. And I collect all that steam. And I let it condense. Does that change? So when it was ice, did that chemical change? No. What was the chemical formula for water again? H2O. So if I have H2O, ice, we typically use S to represent it. S stands for salt. Okay? So we'll draw that little S next to it, right? And put it on parentheses. Right? Salt. Okay? So if I go from a solid to a liquid, is there a change in that chemical? It's still H2O, right? It doesn't change. So, in the case of physical changes, you're getting back the same chemical. It's just changing its state. It's going from a solid state to a liquid state. Okay? So that's an example of a physical change. How you feeling? Pretty good so far? Okay, so let's add a little heat to it, right? Okay, so chemical change. A chemical change means that you're changing the chemical. So for instance, here, I'm starting out with table sugar. Table sugar is called sucrose. Chemical formula for sucrose is C12, H22, O11. Okay, you guys are with me so far? Okay, now as I heat it up, right, and this is the example. I used to make caramels. Love making caramels. I was sweet tooth like crazy, right? And then I was dabbling, I used to smoke a little butter now and then. So I said, oh, we're gonna make some special caramels, right? Yeah. So it doesn't do good. You shouldn't smoke and try to make caramels. So free advice, right? Because what happens is you forget what's on the stove and you continue making caramels. And so what happens, it starts to caramelize. That's what we want. Nice caramel color. You add a little milk, you add cream. That's what you're supposed to do, right? But instead, this is what I did. I sit there and I left it on the stove, right? And instead of getting caramels, I get charcoal. Because at the end, I get carbon and water. The water is escaping as steam. The carbon is left there. So I just get a big old lump of coal. Now, I can tell you, coal does not taste good, right? Have you guys ate a piece of coal before? You ever tried it out? I did. I'm not gonna lie. My dad was barbecuing and I take this coal. You're like, what's it taste like? I mean, taste everything, you know? So, H2O. And C, carbon. Right? So, in this case, this is what happens, right? We started out with this. We broke those bonds and we ended up with water and carbon. This is an example of a chemical change because you're not getting back the same formula. Now I'm going to ask you this. Think about it. You should think hard. Can I make sugar from coal? No. I don't think so. No, we can't. As much as you want to try, no, we can't. shitload of money. Let me tell you, right? The coal miners would love us, right? No, you can't. You can't make sugar from coal, right? No one knows what it is. It's kind of like you burn a log. You get ash. Can you get that log back? No. So those are examples of chemical change. Okay, you guys get that? Okay, so since we're talking about this here, this side of the chemical equation is called the reactant. If there are more than one, it's called reactants. Okay, this side of the chemical equation is called the products. This arrow here, this is called the yield. The yield always points towards the product. Okay, you don't want to use an equal sign, right? Because an equal sign would suggest something else. We're not getting it. We will get it, but not. Okay, you guys with me so far? Okay, now you know this. Capital, 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 right? How many carbons do I have? Oh, I have 12 carbons. So I'm going to write show. How many hydrogens do I have? 22. How many oxygens do I have? 11. Now, if we go to the other side, how many carbons do I have? How many hydrogens do I have? How many oxygens do I have? Okay, so this leads me to the next thing I want to talk about before we start getting a little more chemical versus physical. Now, this here is a chemical equation, but it's not balanced. So it has to be balanced. What do I mean? So there's a law. It's called the law of conservation. The law of conservation says that what you put in, you have to get out. Right? So what you put in, you have to get out. Now this applies to matter generally. So if I put in 25 pounds of sugar, if I add this all up, all together, it should add up to 25 pounds. Okay? Because I started out with 25 pounds of sugar. If I put in 2 tons of sugar, then this has to add up to 2 tons. Right? Okay, the law of conservation says what you put in, you have to get out. That's mass as well as the number of elements. So if we look at this, this does not work out. So then we have to balance the chemical equation so we make sure that it works out. Okay? The way that we do that is we put coefficients. Coefficients are the numbers that go in front of this compound, this element. Okay? It has to make sure that it adds up. So since we know that we're getting carbon out here, we have to have 12 carbon. Right? So if I put 12 carbon here, will I have 12 carbon? Okay, so let's put 12 carbon. So then that gives me 12 carbon. Okay, now this has 2 hydrogens. Right? So what times 2 will equal 22? 11. So if I put 11 here, that will give me 22 hydrogens. And then how many oxygens do I have? Because this number pertains to the whole thing, right? So then how many oxygens do I have? That's 9. Okay? What I put in is what I got. You guys see that?
Well, wouldn't it be the same product? Wouldn't it be back to sugar?
No, because this is carbon and this is water. They're separate. This here, that plus means that they can separate. Right? It means water and carbon. This here means sucrose. This is all together. They're all bonded together. This is separate from each other.
So then that means there's 22 hydrogen, 22 hydrogen atoms, separated from, and then also.
No. Okay, this means that there's 11 water, right?
Yeah.
And so since there's 11 water, altogether, there's a total of 22 hydrogens and 11 oxygens. You see the difference? Where this is one, because this is understood to be one in front of it, this is one sucrose. One sucrose molecule. This is 11 water. Okay, does that make sense?
Yeah.
Don't worry about it, you'll get here in a minute. Okay, so how are you guys doing so far?
I got confused when you tried to explain it all over again.
Okay, don't worry about it. I'll get you back. I promise you that. Get you back. How many of you guys took bio? Anybody take bio?
Biology?
Yeah. Last semester?
Yeah.
Oh, so it should be fresh.
Spring semester.
Spring semester. Okay. So it should be pretty fresh. Okay, so let's talk about biology. Along the same lines, we're not getting too far away. We're gonna help you with this and I'll help you with it. Can I erase this? Everybody got this down?
Yeah.
So far? Okay, so in biology, we breathe oxygen. Why do we breathe oxygen? Hey, that's true. We do breathe oxygen to live. So what does it do at a molecular level?
Oh, it enters the blood.
Okay, you need to go deeper than a blood. You gotta go deeper.
Cells. Contain oxygen.
Cells contain oxygen. So why do your cells need oxygen? To what? You're close. You're pretty close, yeah. And that's something to do with carbon. What was that? Carbon dioxide. Okay, so we'll start. So you guys are getting all the components. So on the reactant side, we're going to put oxygen. Because we breathe in oxygen. And then on the product side, we said carbon dioxide. Because we breathe out carbon dioxide, right? Breathe in. Oxygen. Breathe out. Carbon dioxide. Let me help you guys out. How many of you guys celebrate Thanksgiving? Okay, so what happens at Thanksgiving? We eat a lot, right? So this is how it goes, right? You go, right? Isn't that what happened? I mean, think about it. Watch people, right? And they sweat a little bit and all that stuff, right? What? Why? Right? Okay, so what do you think is happening? Why do you think that big ass breath while we're eating? It has to do with energy. We're going to make energy, actually. We're going to make ATP. It's 32 to, depending on how you count it, 32 to 36 ATP. ATP is cellular energy. Our cells use that. Now, this here is we'll kind of do it like this. This is a special product, right? And it's not made directly from the chemical reaction. It's made because of the chemical reaction first. Okay, we'll talk a little bit about that. Okay? So, we have carbon, right? Carbon. So we must get carbon from somewhere over here too. Where do you think we're getting it from?
The food.
The food, right? That's right. So for us, the best source of food is C6H12O6, often referred to as glucose, sugar. Our cells love sugar, right? Because they take that sugar and they break it down to carbon dioxide and water. So if you notice, you take a big meal, you eat a whole lot, right? You're breathing a lot, right? You're sweating a lot because you also produce heat. So that heat that. So you're producing that heat as well. You notice that? You eat a lot, sweat. I might eat a big meal, sweat like a pig, you know? So glucose. Glucose is being broken down to carbon dioxide and water because the bronze stores energy. Right? That's what's really happening. And this here is called cellular respiration. So this is the chemical formula for cellular respiration. Glucose, oxygen, carbon dioxide. Okay. Now, this here is all going to be energy, so we're going to just take it out for right now, because we're going to worry about the chemical, the balance of the chemical equations. So, when we did the balance of the chemical equations, what was the first thing that I did? Did you guys pay attention to what I did? Other than look cute.
Where?
Can you repeat the question?
With
What was the
balance,
first thing that I did?
the sugar?
Yeah, when we just did the sugar. What was the first thing that I did?
Did you
You
write
see
the
what was
yield?
missing from,
I wrote. Go ahead.
Did you go?
Wait, no.
Is it atoms of separating?
Okay, so I went right in the middle, right? And you were basically, I'll kind of stand what you're saying. We wrote down each of the atoms that are involved in there. So we have carbon, we have hydrogen, and we have oxygen, right? So I wrote a C, I wrote an H, and I wrote an O. You guys notice? Okay? So, then I said, on our reactant side of the equation, how many carbon are there? On the product side of the equation, how many carbons are there?
little sidebar. Will this be in the screen be on the lecture video?
Thank you. Good, good.
Please.
Yes. So let's stop here. So that is like this. See, they really want me to lose weight. They're saying you could be fat, lose weight. So that's why they did this. I know that's why they did it.
Thank you.
They're discriminating against my fat. Okay. So we have one here. Okay. So how many hydrogens? 12. And over here? How many oxygens? 8. How did you get 8? There's 6 here and there's 2 here.
And then what did I get? 3 oxygen?
Over here?
Yeah.
That is correct. Yeah. Because we have 2 here and 1 here. Right? Okay. So, yeah, how you doing? Can I erase this energy part right now? Kind of help us say ATP is cellular. Okay, and I'm going to give us a little more room so we have room to put our quotes. Okay, so the next thing is I need to try to balance things out. I have 6 carbons here, I have 1 here. So what can I do so that I can have 6 over here too? You said 6 in front of the CO2. Yes.
The CO2
And oh yeah, okay, so we can get that. So then that means that we have 12 here and 6 here. We have 6 times 1 is 6. 6 times 2 is 12. And then how many oxygens do I have?
12 and 13.
So 6 times 2 plus 6 times 1.
6. That's each.
Okay, so we have 18. Okay, so we're looking pretty good. So let's just check off carbon and hydrogens because they're balanced, right? Okay, now if we look at our oxygen, 8 and 18. Well, I got 6 here, right? And if I don't want to change this at all, the only way that I can change this is by putting a coefficient on it. So I want to leave this alone. I don't want to touch it, right? Because my carbon and my hydrogens are good. I don't want to mess with that oxygen. Okay? So let's just go ahead and subtract 18 minus that 6. What is that? 12. Sure enough. Okay, 12. Okay, so what can I put in front of here so that I end up with 12 oxygens? There's 2 here. What can I multiply? 6. That's right. What can I multiply by? to make 12. 2. So let's add that up. So we have 6 plus 12. Does that equal 18? Okay. 18, 18, 12, 12, 6, 6. No.
But did it change the reactant?
No. I didn't change the reactant. I changed the coefficient, right? That's right. So the coefficient can change. The chemical compound can't. Okay? So you can't change this part. You can change this
And is that taking your answer?
part. Okay, you're saying I can change this?
No, what's on the left? So for example, the C6, if it was worded how the oxygen was worded, you could change it if it's on the left of it.
Yeah, I can put another number here. Let's say if there was a different compound, we'll do another example in a second. But I can put a coefficient in front of it. Yes. Yes. Yeah, but in this case, I didn't want to because then that would change how many you have. Does that make sense?
Yeah, and then also, because you know how I did it breakdown with the words and you subtracted the 18 with the 6.
Yeah.
So in that case, you could always subtract the 18, what was left over.
Yeah, if you have, like in this case, we have oxygen over here, and we have oxygen over here. You have 2 sources of oxygen. If everything else is already matched up, just take this one out and see if you can get this one balanced out. Okay, does that make sense?
So in this
You okay?
case, all right, we took out the 6.
Yeah, so we looked at the other side, right? And we said there's 18. So if I took my 18, I knew I had 6. Because I don't want to change this, right? Because right now, if I put a coefficient in front of you, right, it's going to change everything, right? And we don't want to change everything if everything is looking almost right. And we can get away with just changing this. Do you understand?
Yeah. But then if you change, didn't you take out of the reactant then?
No, I did take out the reaction. It's still part of the reaction. It's still here. It just helps me get this number. Right? Because this is going to be accounted for regardless. There's 6 here, right? If I don't put a coefficient here, right?
Oh,
There's 6 oxygens.
yeah,
Right?
I kind of did it. Yeah.
Yes.
The part of it is like with the state.
Yeah.
Earlier, exactly, you're talking about the state, like relating to the state from one chemical to another. So that's so different from showing us the.
Yeah, because in the state, there's no change in what's happening. Right? Here, this is a chemical reaction, right? Chemical reactions, you're changing what you're getting on the other side. Right? And so you're given, and usually you're told what you're going to make, right? Or when you guys get good enough, when you guys learn enough information, you'll be able to say, okay, this is what I'm going to get from this type of reaction, right? Because there's only so many types of reactions.
So basically, it's the right side is what happened, what you got, or what you're saying to the left. Like by you putting that 6, it's saying it's what you need. It's what it's what you need to have.
This part.
Well, for this chemical reaction, this is how many oxygens are there
Balance out, right?
to balance out. Yeah. So because at the end of the day, what you put in is what you have to get out. Right? If I left it alone, it would have been balanced. Right? And that means that the reaction wouldn't happen. Does that make sense?
Yeah.
Okay. Okay, you guys ready for another try? Right? Okay, or you guys want to take a break and then we'll come back.
My brain's already on the
Okay, we'll do one more and then we'll take a break. And then we'll do a couple rounds. Okay? Is that fair? Okay. So we'll do something very simple.
How many years have you been teaching chemistry?
Let's see. Really? Officially teaching chemistry? Or are you talking bootleg, other people pass on later on? So I've been teaching, technically, if you're talking bootleg, I've been teaching since I was in, I guess it was junior in high school, right? Because I would make money on the side by teaching other people so they would pass classes. I was actually teaching college students how to do chemistry when I was in high school. Right?
So that's your right. How did you or how did you at a young age?
It's math. It's all math. If you look at it, right? If you look at this, it's math. That's what it boils down to. And I was always good at that. And then I got really interested in chemistry. Well, I got interested in chemistry in the early 80s. My mom got me a microscope when I was a little. That's how I really got started. And then I started playing with chemicals, and doing things I probably shouldn't have been doing. And let me tell you, I've done a lot of things, right? So I paid my way from calm by making alcohol and selling it, Oh yeah, I made wine. I made wine. I didn't make moonshine, I made some wine. And so I would sell bottles of wine to friends of mine when I was in high school. So that I did enough money. I was telling my dad I was mowing lawns, right? And he said, for somebody who's mowing lawns, and it wasn't until I guess I finished college, I graduated from college, he found my little rig and stuff, and he found like I had a couple bottles saved. And back there, I was pretty good. It was all nice and clean. I learned real quick. So I went to the library, and man, you can find a book on anything. Now we can do it all on YouTube, right? So found a book. I'm like, okay, did the calculations, figured it out. I'm like, okay, tried it once, worked great. Okay, now I need to make it pretty. Learn how to make it pretty. Okay, so it was a piece of cake.
So you sold beer or
It was wine.
wine?
Yeah,
Like
just
straight
wine.
wine? Or what kind?
It was a lot of it was grape wine because we had a grape tree on the back, and we had an orange tree in our back, a grape vine in our backyard. And so I take all of the grapes out. And that's like, this is not growing 80 oranges. It's like I was wanting some oranges the other day. So and oranges are really hard because if you either have to kill them all, right, and just use the yeast that is on the inside, but if you use the rye, it kills the yeast because it has an application that kind of kills yeast and stuff. And so it was really, really hard to sit there and do the orange and take forever. The grape juice, like, it's
Not even.
piece of cake. So if you guys happen to take Chem 1B, you learn how to make wine. And then if you guys take OChem, you learn how to make hard liquor. So it's simple. I gotta keep you guys coming back. Okay, so let's use method. I'll let you guys go in and we'll talk. So.
Is the product the same for nothing or initially? Yeah. Okay, so
Let's say the same numbers as last.
okay, so it's in wording. Okay, yeah, I got it.
Like going over things. I can see those gears are turning. Yeah. So.
So stick around. Chapter was left over on the other side. Chapter 6 on the right side, six, so I have two. They put the three here, this is six. Yes. I think we have the last one. You guys remember how, I think some chapter was left over on the other side, on the lower side. This was the sticks I think it will be, I think this will be awesome. This? Yeah, I think I would just find out the easy. Yeah, that's what I'm saying. One plus. Okay. So then, are we good? Right. What about ions? 4. Okay. So then, how do you? Okay. Everything is sure. Okay, so remember this plus I'm ready to do this. You got it? Yeah. So you guys want to do it? Oh, yeah, I know we do that too.
Okay.
Yeah.
Okay, so let's go over together. Are you guys ready?
Oh, yeah.
Okay, so how many you got it? You guys got it?
Go ahead.
No, okay. Okay, you guys want to give it a shot? Okay, so how many carbons do I have on the reactant side of the equation? 1. How many hydrogens do I have on the reactant side of the equation? How many oxygens do I have on the reactant side of the equation? 2. Okay, so we go across the yield side, right? Now we're looking at the product side, right? So, how many carbons do I have on the product side of the equation? How many hydrogens do I have on the product side? How many oxygens do I have?
3.
3. Everybody sees that. There's 2 here and there's 1. So 2 plus 1 is our 3. That's how we got 3. Okay? So is it balanced? No. So since it's not balanced, we need to put coefficients in to balance it out. So what am I going to put my first coefficients? Okay, look at our carbon. It's 1 and 1. Are we good at carbon?
Yeah.
Okay, so we're just going to put a check mark, right? We're good at carbon. Okay? Now, hydrogen. Are we good on hydrogen? No. So I have 2 on this side of the equation. What can I put in front of here so that I'm going to 2? Okay, so then that gives me 4. And my oxygen changes. So, how many oxygens do I have now over here with water?
2.
I have 2. So 2 plus 2 is 4. So now we have 4 oxygens. Okay, now this is my only source of oxygen, right?
Why does it add on to
Yeah, because these guys are attached. The coefficient is being distributed. Okay, because they're attached. That's 1 all together.
okay.
That's right. Yeah, so it's multiplied by both. Okay.
Any coefficient, where are they called? What is that called?
This here, H2O, is called no. Right? It stays together. Water is always H2O. You can't change what water is, right? You can only change the coefficient. You can only add more water. That's right. That's exactly it. You got it, right? Yes. Oh, that's right. That's good. I'm glad. Everybody got it? Yeah. That's good. That's good. Okay, so then, how many? 2. Okay, so that gives me a total of 4 oxygens. Good? Okay, so let's take a break, then I'm going to blow your mind. Okay, so, couple of things. This here's ethane. Ethane is a gas. So when we're writing chemical equations, we often will say the state of them to help us understand what's going to happen with the reaction. Oxygen is a gas. So we'll put a G here. So G stands for gas. Then what we get out is going to be carbon dioxide, and we're going to get steam, water, right? So it's going to be a gas. So this here is called a combustion reaction, right? And so it's important to understand what type of reaction you have, because if you understand what type of reaction it is, then you can kind of figure out what the products are going to be, right? These are kind of understood. Anytime you have a combustion reaction, an organic combustion reaction, you're always going to end up with carbon dioxide and water. Okay? Except in the case of when you don't have the oxygen available, or if you add just pure sugar, if you let it cook long enough, you're just going to end up with carbon and water. Right? That's what we saw earlier. A combustion. I'll spell COMBUS. Combustion. It's a combustion reaction.
Every time there's a combustion reaction, there's always going to be carbon dioxide,
And water. Yes. So let me clarify that a little bit. So anytime you have what we call an organic compound, organic compounds have carbon and hydrogen. And okay, they have hydrocarbons. They have hydrocarbons. Okay. So carbon and hydrogen. So that's going to be an organic compound. Okay. So anytime you have an organic compound, something that's hydrogen and carbon in it, then you're going to end up with carbon dioxide and water. If you have oxygen there. Okay? All combustions like fire needs what? Oxygen, right? Because it's burning carbon and then hydrogen, right? Okay. So let's do this one. This one's a little tricky. Okay, but it's the same process. Same process. I want you guys to see if you guys. Well, we'll do it together. We'll do it together. Okay. So, how many carbons? Two carbons. I should say on one side, huh? Okay. How many hydrogens do we have on the reactant side?
Six.
How many oxygens do we have on the reaction side? Okay. We go on our product side. How many carbons do we have?
One.
How many oxygens do we have? And how many hydrogens do we have? Okay, is it balanced?
No.
No. Okay, so where should I start? What was that? With the carbon. Start with the carbon. Okay, so I have 2 here and I have 1 here. So what is the coefficient I need to put in front of carbon dioxide? 2. Okay, so I want to make sure that you guys understand this.
Yeah.
We put a 2 here, right? Yeah. So then that means there's 2 carbons and there's how many oxygens? 4. And it only pertains to this because as soon as you get that plus means that there's something else. They're not connected. They're independent of each other, right? Okay, so that's what that plus means. It means like and this, right? Okay, so they're independent. So this 2 only pertains to this compound. Okay? Okay, so let's do that number. So we have 2. This is 4 plus 1 oxygen. So that's a total of 5 oxygens. Do you guys see that?
Yes.
Okay? So we got 2 times 2, 4, and then we have the 1 that's right here. Okay? So, what's next? The hydrogens. Okay, so we have 6 here, we have 2 here. 3. Okay, so if we have 3 times 2. Okay.
3 times 3.
And 3 times 3, so now we still have the 4 from here. Now this here is now a 3 for the oxygens, 7. Okay, so now I want you guys to think about this. What can I multiply 2 by to get 7?
3.5.
3.5 or 7 halves. Same thing as 3.5, right? So I'm going to put 7 halves in there. You guys, God damn it, we have to do that fraction, right?
Yeah.
Okay, so now I want you guys to think. Okay, Mariah. Okay, so if I came here and I cut Mariah in half, what would happen? Would she be okay? No, she wouldn't be okay, right? She would be screwed, right? So the same thing happens with the molecule. It's together. If we cut it in half, we fucked it up, right? So we can't have a half of the molecule. So how do we get rid of halves? So if you have something on the denominator, how do you get rid of that denominator?
If you add
Don't add it. What did you say? You multiply. So we're going to multiply everything by what? What is our denominator? So we're going to multiply it by 2. So we're going to multiply the whole thing by 2. This whole equation. Do you mind if I erase some stuff up here so that I can rewrite my equation?
except that.
It's too late now.
No.
You mean combustion? Oh, you don't want to?
The word, the
Okay.
numbers. I know.
Okay?
Is the 7 over 2 still there?
No, because we multiplied it by 2. We multiplied all the coefficients.
You took away like the two dividing that one's the.
So like,
You took out the two from the bottom that one.
Oh, yeah.
So the top
I
three
get it.
added that,
Yeah.
you skip on the middle.
Yeah.
Yeah.
And then those two cancel out.
Yeah, he skipped all that at the two.
okay?
And that can all this.
And what was the reason for that? So,
Because we can't come around in half, right? So if you have a half, something over a half, that means something is going to be cut in half. You can't have that. You can't cut them all. Technically, you can't cut them all in half. That's your chemistry. It's a whole other world. That's not. Yes, you guys are rookies. Okay? Are you guys, how you feeling? You're confused? It's okay. No. Here's an opportunity to stop for a little bit. We'll stop for a little bit. We want you guys to think about it. So what is it that you're confused about? Where did I lose you?
Oh, you lost me at the balancing the 6 with 2. And then from there I lost. So from there I just.
Okay, so you were good. You said when we got to the 6, you're like, okay, I got it, right? Or you were lost before that.
No, right there.
Right.
3.
Okay.
That's where.
So
it's
when we
from
put
there.
the 3 here, yeah, we're gonna get our 6, right?
Yeah.
Okay, so then we needed to calculate our oxygens, right? And that's what I think you're having a little trouble with, is that oxygens. Because there's 2 sources of oxygens on our product side, right? So we have oxygens over here, that's right, and we have the oxygens over here, right? So this is the coefficient for this oxygen. So 2 times 2 is what? It's 4, right? That's for that oxygen, okay? Now, 3 times 1 is 3, okay? So 4 plus 3? 7. So that's how we get our 7, okay?
Okay.
So here I have 2 oxygens, right? Since I have 2 oxygens, whatever I multiply this by, right, it has to equal 7. Well, the only thing that I can multiply this by to equal 7 is 7 halves, right? Plus 7 halves times 2 equals 7, because the 2's cancel out, and we end up with just 7.
I got it now.
You got it now?
That little part was.
Yeah. And it happens, it's like this, and sometimes you just gotta just slow me down, it's okay.
Thank you.
I'm here to ask and answer questions, and sometimes I'll ask questions. Okay, everybody's good?
No.
No? Okay, so what is it that you're doing?
Okay, so the 3.5 equals 7 halves.
Yes,
I don't think that's.
3.5 equals 7 halves?
Oh, can I explain that?
Okay, so
So you pack up an atom or anything in half, so you have to use whole number. So that's why he multiply everything by 2, so I need to even out like basically.
Oh, so you're just using that as a reference.
yeah, so if you do me a favor, so when you guys look at fractions are just division, right? That line just means divide. So on your phone, you have your phone available? Go to the calculator, type in 7 divided by 2. 3.5, right? So that's where I got 3.5, right? Because he said, oh, 3.5, because if you multiply 3.5 times 2, it's 7, right? So that's where we got it from. And then I said, here, because we can't have a half of a molecule, right? You can't cut a person in half. You can't cut a molecule in half and have that same molecule. So we need to get rid of that half. So the only way to get rid of that half is by multiplying everything by 2, right? to get rid of the denominator. And so it's easier if we have a fraction, because then you know what you need to multiply everything by. If you use 3 halves, unless you do a little bit of math, you're like, oh yeah, I need to multiply it by 2, right? Does that make sense? Yeah. So let's say, for instance, I had 3 here, right? Instead of a 2. So let's say it was ozone. O3 is called ozone. You guys heard of the ozone layer? Right? O3 is called ozone. So if we had a 3 here, it would be 7/3, right? Because we're multiplying everything in this case by 3, right? So we need to get rid of that 3, so then that would be 7. So again, now we have to multiply everything by 3. Okay? Yeah, so for everything to be equal. Okay? Does that make sense? Yes.
When you're multiplying everything by 2, are you just multiplying the thing that we got stuck on? Like,
no, the whole equation. So you know this, yeah. Yeah, so here, this, the ethane is multiplied by 2. This is multiplied by 2. Let me take a slash 2 so we don't. That's how we got our 7. This is multiplied because it's 2 here, multiplied by 2, right? And then this green is also multiplied by 2. So everything is multiplied by 2, right? So if you do, it's kind of like it's math, right? You guys remember, if you do it, you got to use the whole equation. You can't just do it to 1, right? It's the same thing. It's just math. Don't overthink it. It's just that math. Don't be scared of math either, right? Okay?
Well, that's a whole nother.
That's a whole other story.
That's a whole nother class.
Okay. So how do you guys feel? Okay. So I'm going to give you one that's going to be a little challenging, but I want you guys to do that. Okay.
But it's not balanced, right?
It is balanced.
Yeah.
You want to take it out? Oh, let's take it out. We want to confirm it, right?
Yeah, I want to
break it down again?
Yeah, I want to do it for one. Get it all like balanced.
Okay, so I'm just going to erase this part right now. Give us a little room to work. Okay, we're going to write it in red. Okay. Okay. 2, 4. So I have 4 carbons. Okay. How many hydrogens?
6. No, sorry, no.
12. How many oxygens? 14. Okay, over here. How many carbons? 4. How many hydrogens? 2, 12. And how many oxygens?
14.
Is it balanced? Okay. Good job. Yeah. Okay, you ready for the next one? I'll give you time to write it down. Before I erase it, because I am quick on the gun. Yeah, that was just make sure we're working.
They always confirm this.
What do you think about work? So if there's stuff added onto it, then you just gotta make sure everything's balanced. Make sure you, don't worry about it, we're gonna make it happen. Okay, you guys ready? Okay, ready. Did you not get it done?
She was saying she's hot.
Oh, okay. It's hot in here, right? I thought it was just me.
No, it's so hot.
Exactly. Okay, so I'm gonna introduce another, it's not really a state, but it's called AQ. AQ means that it's in water. It stands for aqueous. Yes, aqueous. Means in water. Okay? So we have that's an L. Okay. Okay, you guys ready? First step.
First thing, write them down.
Write them down. Okay?
The AI or the AR?
AL. AI would be, remember, if it's A, it's not A type of one. It's, I get it, yeah. It's AL, yeah, it's A. I need to make my UPL or something like that, right? Yeah.
In the periodic table, it's also just like a.
It's an L, yeah. Yeah.
So if we write it like that, we won't get
You
it.
won't get, yeah, I
Okay.
know that what you guys need.
Okay.
Right? And plus, there's no element, if you guys look, there's nothing that is just A. Right? Look at your table. There's nothing that's just A.
So AL by itself would be aluminum, right?
That's right.
I'm learning this stuff, like, I'm just thinking out there, I'm actually learning.
Yeah, it's good. You guys, I love it because you guys are smiling, you're so excited. You're like, I don't get it, but I'm getting this. You know, like,
Yeah.
okay, yes. That's right. That's right. Exactly. Yep. Okay, so as we talked about earlier, this means there's 3 of these guys inside of it, so it's going to be distributed. So it's going to be 3 times 3 here, and in this case 3 times 4. Okay, so let's start getting the numbers. So how many aluminums do I have? 1. I have 1 aluminum. How many nitrogens do I have?
3.
I have 3. And I have 9 oxygens plus, okay, so 9 plus 8, 17. Okay, and then magnesium. I have 3 magnesiums and phosphorus. Man, you guys are, I'm tired. Wiggle. It's because it's hot in here, isn't it? Yeah. See, that energy, it's moving fast, right? Okay, on the other side. Aluminum?
One.
It's 1. Nitrogen?
2.
2. Because we know that that's distributed. Okay. Oxygens? Yeah. So we have 2 times 3. The 6 plus 4. 10. Did you say 10? You said 10. Okay. 10. Okay. Okay. And MG? And P?
1.
1. Okay. Okay. So, where are we going to start?
Top to bottom, so
Okay.
AL is good.
AL is good. Okay. What about nitrogen?
So you gotta, I feel like you gotta multiply by 2 equals 6. Like, so the 2 will be times 3, and then the nitrogen, the one on the left will be times 2, so they could equal 6.
Okay. So I need to put a coefficient in front. So you're saying I need to put a 2 here.
Oh, but it's the same range, so we're good.
Okay, so if I put a 2 here, that's all right. So if I put a 2 here, is that what you say? Put a 2 here. So then that means that we have 6 here. And then you're saying I put a 3 here. Right? Yeah. Okay, so then that gives me 6. Okay, so that changes my aluminum. My aluminum is now, how many aluminums? 2. Okay. And then also over here changes my magnesium. How many magnesiums do I have now? 3. I have 3. Okay. It also changes my oxygens. Look at the oxygens over here. So now we have, so 3 times 3, 9 times 2, 18. Plus 2 times 4,
80. 26.
26. Okay, and then over here, I have 2 times 3 times 3 plus 4, 22. Okay, so are we good? No. Okay, we have 2 aluminums. We have 1 aluminum. Let's go back to that. So how can I make it so that I have
You add multiply 2 on the.
so put 2 here? Okay. So then that gives me how many aluminum? 2. Okay, so let's look at the oxygen now. I have 2 times 4 plus 6 times 3, 18. So then that's 26. Okay, and then how many phosphorus?
4, 8.
What's next to it? It's a
Oh,
1.
2.
Okay, so I got 2, 2, 3, 3, 26, 26, 6, 6, 2, 2. Is it balanced?
Yeah.
Okay, not too bad.
A little.
It's just a lot, right? A lot of oxygens. 18 plus 8 goes 26, yeah. I wrote it up here, and I forgot the 2. The heat's getting to me now.
Overheating.
Yeah, I'm overheating. I'm burning out of it. You know. Yes.
So are you going to allow will be the coefficient of the 2 and the 3?
That's right. So that'll be it. Okay.
Thank you.
Okay. So let's move forward. All right. Don't worry about it. We'll have an opportunity to do a lot more of these. Yes, and you got a homework. And your homework assignment is up. Okay. Okay. Here we go. Okay, so physical versus chemical. So that first picture, okay, that's a log burning. A log burning. Is that a physical change or is that a chemical change? Chemical change. Okay. An icicle melting. Physical change or chemical change? Okay, crack that glow stick. Chemical change. Right? Why is it a chemical change?
Because you can't turn it back to not moving.
Okay.
Good.
Yeah, okay, that's good. Well, it'll eventually stop going. Yeah, it's just burnt out. But yeah, that's it. Okay, so the next thing we're going to talk about is pure substance. So something is considered to be pure if it's all the same type of matter. It's exactly the same type of matter. So if we only have H2O, it's called pure water. Okay? If we only have pure sucrose, that's the table sugar. Right? Pure, it's only that. Now, if I added salt to my sugar, it's a mixture. Okay? So, wait, can you tell the difference between salt and sugar? No. So, since we can't tell the difference visually, it's considered to be homogeneous. It looks the same. Homo, like homosexual, meaning the same sex, right? Heterosexual, meaning different sexes, right? Okay, so homogeneous. I'll write it on the board. Did you guys get this down? Yeah. Brackets fill. So homo meaning the same, homogeneous, so it's the same throughout the entire mixture. Okay? Heterogeneous. Is different. Okay, so let me give you guys an example. Have you guys ever put orange juice and milk together?
No.
Orange juice and milk.
I couldn't imagine it though.
You can imagine it makes like a little rain. That's a homogeneous. This could be a heterogeneous. Right? Right? Delicious.
Yes, like the protein.
Yeah. Okay, now we know that homogeneous means the same. So, for instance, have you guys seen rum and Coke? Yeah. So it all looks round, right? So that would be homogeneous, right? If I put salt and pepper together, is that homogeneous or heterogeneous? That's right, right? White and brown, so it'd be heterogeneous. Yeah. Okay? So a mixture is something that consists of two or more pure substances.
So then there's two types of mixtures, right? Either a homogeneous mixture and
Yeah, so if you guys, they will often say homogeneous. A homogeneous milk is homogeneous, right? Homogeneous milk. So it's pastured and homogeneous. That means it's all looks the same. But if milk powders, right? You get some of it that's liquid and some of it that's heterogeneous. right?
Would that be like condensed milk or no? That's
No.
That's the home.
That's the homogeneous.
So what would be like an example?
Like if your milk spoils.
Oh,
Then that
then
is-
that would turn into a.
Yeah, so then that would be heterogeneous, right? Okay, so often when we add things or add mixtures together, so if we add salt and water to it changes the properties of that solution. So water boils at 100 degrees Celsius. If I add salt, salt causes the boiling point to increase. So instead of boiling at 100, it'll boil at 105 or 110, depending on how much salt I add. How many of you guys cook pasta? Everybody cook pasta? Okay, why do you add salt to pasta? So it cooks faster, right? So you guys say, so it boils faster. It's not because it boils faster, it cooks faster. So why does it cook faster? And why do you want to cook it faster? Because you're hungry. Okay, that would be a damn good reason to cook it faster, right? It would not be there, right? So, well, it's gonna cook faster because now you've got a salt. That changes the boiling point. So that means that the water is actually hotter. Right? So the water isn't able to evaporate as much because the salt is there. Okay? So that means that the water's hotter, you add the noodles, and now you don't get soggy noodles. So if you watch, if you guys put one thing of salt, one pot of salt with water, and one without water, right? Boil them together. Put the noodles in there at the exact same time. Your noodles that don't have salt will be much soggier than the ones that do have salt.
I thought it was super left.
Yeah. No, but see, it also helps with seasoning too, right? It's hard. Salt makes everything taste better. Okay. Also, you can have blood pressure, but you know,
Yeah.
prices will pay for good things, right? Okay, so if we take a look at, we have pure bromine. Pure substance, is that homogeneous or heterogeneous? Homogeneous. Because it's pure, right? It's going to be exactly the same. Actually, not really even homogeneous, it's a pure substance, right? If we have pure water, is it a mixture? Water? Pure water is a mixture? No. It's a pure substance, right? Now, if I add bromine to water, is that homogeneous or heterogeneous?
Heterogeneous.
Okay, now it's what we see. What we have seen. Does it look exactly the same from the entire thing? Right? So is that homogeneous? Okay, if I have a whole bunch of bromine and a little bit of water, is that homogeneous or heterogeneous? Homogeneous. That's if you look at it, it's almost the same, right? That's right. Just the intensity. Okay? Get your questions. Ask your questions. I'm good at this. Okay, so we talked about heterogeneous, we talked about homogeneous. You guys feel comfortable with it? So homogeneous, uniform appearance. It's exactly the same throughout the entire. Heterogeneous means it looks different as we look at it. Okay. Now again, we're looking about our visual appearance. That's what we use to sit there and dictate whether it's homogeneous or heterogeneous. Right? Because we already know it's two mixtures of things, right? Okay, so this is just another example. If I have alcohol and water, well, you know what that is, right? It's a diluted drink. I use it all the time to sit there for my family. Because a lot of it way too much to keep that house at home. So, and they can't tell the difference, right? Because they're drinking so much, it's just like, you know, maybe they taste it like, you bought that bad stuff this time. So, okay, so we can use physical properties to separate mixtures. Okay, so an example is if I have iron and sulfur mixed together and I run a magnet over it, I'm able to remove all of the iron because the iron binds to the magnet where the sulfur doesn't. Okay, so I use the property, the fact that iron is magnetic where sulfur isn't. So I'm able to use physical properties to separate it. So you guys can actually do this experiment with cornflakes. Cornflakes has a lot of iron, like literally iron. So you crush up the cornflakes, you run a magnet over it, will collect.
Is that bad?
Well, you need iron.
So like that type of iron.
Yeah, you do need that type of iron. Okay. Oh, really? Yeah. Learn something new every day. Yes, and we like to tell me about food all the time. And aren't you guys getting hungry? I'm getting hungry. And some of you here are like, what's open? And they're like, Burger King. Damn, that fries over there. Okay. Another means of separation is distillation. Distillation is the process of using the boiling points, different boiling points to separate different things. So we talked about that hard liquor, right? So the way that we make hard liquor is by distillation. Water boils at 100 degrees Celsius, where alcohol or ethanol, right, boils at 89.6 degrees Celsius. So as long as we don't get that 100 degrees, we stay between that 89.6, we're able to sit there and distill off the alcohol. I'll show you an example in a second. Okay, and the other one is filtration. Filtration, how many of you guys are talking? The old-fashioned, not the parade. Everybody says, what? Coffee? Really? So what do you guys use to sit there and separate the grounds from the coffee? A coffee filter. That's just a form of filtration. Okay, so distillation, if you guys take a look, we're heating up some water here. Technically, the water alcohol. The alcohol is going to evaporate out. We're going to cool it down, and then we're able to collect technically the alcohol. Okay, now this works for that distilled water too. So this is all just water. We boil up that water, we cool it down, and we get pure water. And then we do all of the minerals and stuff. Okay? Okay. Yeah. Is it time? Is it time? Yeah, goes by so fast. We're almost there.
And it was forget.
Okay, so we talked about that coffee filtration, right? So we have solid and liquid here. We put it in that filter, and then we just get that pure liquid homogeneous solution. Right? Coffee. Spilt wine today. Again, this is the third time I spilled coffee coming in. Yeah, again, win. So by this time, I already, already passed out. Okay, so now we're going to talk about elements, compounds. I know it's time to build, but we're going to use this word. Elements, compounds. Okay, an element can't be broken down chemically. It's just that element. That's all it is, right? So I want to talk to you guys about diatomic elements. You guys have your periodic table available? There are 7 diatomic elements. Okay? We're gonna have to do this first. Okay, 7 diatomic elements. We have hydrogen. Nitrogen. Chlorine. Oxygen. Chlorine. Iodine. And bromine. Okay? The way I remember it is have no fear of, oops, I screwed up. There. Ice, cold beer. Okay? Have no fear of ice, cold beer. So these are your 7 diatomic elements. Diatomic, di meaning 2. atomic meaning atoms. There's two atoms. H2, N2, F2, O2, I2, Cl2, and Br2. Yes.
How do you spell diatomic?
Diatomii. Diatomic elements. Okay. If you also look at your periodic table, if you go nitrogen, oxygen, fluorine, all the way down to iodine, it makes a 7, right? You have a periodic table, and then you have plus 9. Right? So, okay, so those are your 7 diatomic elements. Now, what do I mean by diatomic elements? In nature, naturally occur, right? Sorry, I can move out of the way so you guys can see. Naturally occurring. These guys, if they're by themselves, they're going to be in twos. Okay? So oxygen gas, right? It's going to be O2. That's the reason why we have to write it as O2. Okay? Fluorine gas, we have to write it as F2. Hydrogen gas, H2. Now, when they're in substances, when they're in things, they don't have to have 2. They can have how many you need to make that compound. Right? Yes, got that?
Yeah.
Okay, there are 2 polyatomic elements. There's phosphorus, which is P4, and there's sulfur, which is S8. And that's it. Okay? So we got 7 diatomics and 2 polyatomics. Okay? Now, the definition of a molecule. It's 2 or more atoms bonded together. Okay? So, sodium chloride, or salt. Is that a molecule? That's 1, that's 2 atoms. 2 or more, right? Phosphorus, P4, is that a molecule? It's also a polyatomic element. It's both. It can be both. It can be both a molecule and a polyatomic element. Okay? Sulfur. Is it a molecule? Okay, a compound. It's 2 or more different atoms bonded together. Okay? Okay, so are these guys a compound? No, because they're not different. They all have, right? They all have the same atom, right? But they're molecules, and they're also elements. Is that a compound? It's a molecule.
But they're not different.
Okay, but they're not different, so it's not a compound. Okay, it's also a polyatomic. Sodium chloride. That's a compound. Is it a molecule?
Yes, it has 2.
That's right. H2O.
Yes.
It's a compound.
And molecule.
And a molecule. Sodium. That's just an element. Okay, piece of cake?
Is it a compound? It's not a compound also? The.
Sodium? No, because it's only one by itself, right? We're almost there. Question, I know. Okay, so this is just showing us mixtures can be separated by physical properties, physical means. A compound can only be separated by chemical means. Okay? These are some examples. We won't go too far into it. That we see in nature. Right? So we've already talked about the element and the symbols that we use for 1 or 2 letters. We talked about chemical formulas. Right? We talked about the atom. We talked about the molecule. Okay, this here is the law of constant composition. I think I'm going to stop here and we'll pick this back up on Thursday. We'll talk a little bit about it. What's that? No, we're going to check it out because we're doing a lab on Thursday. Next Tuesday. We'll be Thursday, right before we finish this up.